Okay, so for this last video, I want us to talk a little bit about design decisions and the map ADT. And we're not going to have a whole section on design decisions, partially because I mostly just wanted to bring something up real quick so we can do a practice problem about it in today's class. But, and then the second thing will be we're going to reintroduce the map ADT. And I say reintroduce because you probably saw this in 143, hopefully, or at least remember that name. But again, we're going to do this for review and dive a little bit deeper. Okay. So I want to quickly reiterate what we've learned so far about ADTs and data structures. So far we've seen that an ADT can be implemented by multiple data structures. The list ADT can be implemented by an array or by linked nodes. Both of those are completely valid implementations. Each one's its own data structure. It can implement that ADT. Also turns out a data structure can implement multiple ADTs. As we've seen in all this lecture, we've been kind of doing a little bit of deja vu, where for each of these data structures, we've had an array implementation and a linked list implementation. So one data structure can fit multiple ADTs, just like one ADT could have multiple data structures that implement it. Do be careful, though. One of the things that's important about separating these ideas, the idea of the ADT from its implementation, is it allows our discussion to be more generic. When you talk about things as a list, you can ignore if you're using an array or a link structure. You just have to focus on the list-like behaviors. But because one data structure can act as act in place for multiple ADTs, and each ADT has its own set of requirements of what methods and behaviors must be provided, then it's probably the case that if you're using, say, a linked node as a queue, that it's going to have extra methods that the queue didn't want. For example, getting something at an index. And so if you're truly using something like a queue, you should only use its queue-like behaviors, adding at the end, removing from the front, even if the concrete data structure provides more behaviors. And that's because we want to keep our discussion generalizable. We want it to work for any queue if we're talking about queues, not just one specific type of queue. So with that, we'll come back and talk about ADTs and, actually, one more thing I want to say about this. One of the things I mentioned in class on Friday during our practice time was one of the big important tasks when using a design decision to solve a problem is first starting by choosing an ADT that you're going to want to use to model the situation. Like in that Dub Street Burgers example, I first said, let's model the line of orders as a list ADT. That's always a first decision you have to make. What ADT am I going to try to use here? Then there's a second decision after that of which implementation of that ADT am I going to use based off my context. And so it's usually helpful to sometimes think about this two-step process when trying to decide how you're going to represent your data. Okay, so now going back to the map. Let's review what a map is. A map represents a set of distinct keys or unique keys and a collection of values where each key is associated with one value. This is sometimes also called a dictionary and some other commonly called a dictionary in other programming languages, and sometimes the ADT is called dictionary instead. But we're going to mostly call it a map for most cases, but sometimes I call it dictionary because I'm a Python person and they call their maps dictionary, so sometimes I mix it up. I'm sorry about that. One of the key things about maps is that the key already exists, then you overwrite it. So if you put a key twice, you're going to overwrite the old value with the new one. And so the map ADT, we call all of its behaviors just like the Java versions of the method names. So put, get, contains, key, remove, etc. Maps are going to be a programmer's best friend. Usually when I'm trying to solve problems, maps are almost always the first tool I think of when trying to solve it. It's hard to work on a big project without needing one sooner or later. Personal opinion, but I think one of the reasons that Python programming language has gotten so popular at data science is that it makes the syntax for using maps or their dictionaries just so simple. It allows lots of power with relatively little syntax. Unlike Java, which is very verbose, especially when it comes to maps. So in 143, for example, we introduced how you make a map. You say map, and then you put in the brackets for the type, string, and integer, and then you choose the implementation. In 143, we taught you two implementations of the map interface, hash map and tree map. Don't worry, we'll come back to hash map and tree map later in the quarter to talk about how to implement them. Today, we're going to go with much simpler implementations of the map ADT so we can talk about some more ideas. And probably, no big surprise, we're going to talk about array-based implementation and a linked-based implementation. Let's go ahead and do it. Before that, I want to mention one quick thing about maps in particular. There are lots of ways to think about how a map might represent its data. A lot of times when we think about ADTs, we like to picture something in our head, some abstract representation of what data are we storing. And in the history of since maps have been created, there have been lots of creative ways to try to picture what you think a map might look like. Some people think of these maps as being like this kind of text-based where you have keys and values. I forgot a comma there. I'll add that in before I post the slides. Some people think of it as being like a set kind of thing of key-value pairs. Some people think of it as being a set of keys that then get mapped to some set of values. All of these are just abstract pictures that you can use in your head to think about what's going on. It's important to highlight that these are just abstract. They have no indication of how the map is actually going to be implemented in one of its concrete data structures. It turns out that all of the data structures we're going to talk about that implement this map ADT have nothing to do with these pictures. They don't look anything like this. And so it's sometimes easy to get mixed up. You're like, oh, well, where is this picture in my concrete data structure? This is just an abstract picture. Okay, so our first implementation is using an array. It's not going to be any old array, though. We're going to make an array of key values, pairs. So each array entry is going to be a pair object, and a pair object is just a common terminology for an object with two fields that you can store two things at once. What we're going to end up doing is we're going to store this array of key value pairs and a size in order to implement the idea of the dictionary. One notational thing, we usually use these brackets inside our ADT descriptions to sit whenever we have like generic types. And so I'm using K and V here to be like a placeholder for the key type and a placeholder for the value type. So just wanted to mention that that's a thing there. So the behaviors, the way we implement those behaviors with this array map is put needs to find the key. So you first start by finding the key, which means you start at the beginning and loop through until you find that key. If you already find a key there, then you just overwrite the value. You don't need to make a new key value pair because with put, if the key already exists, you just associate it to the new value. Now, if it's not there, you're going to have to go all the way to the end of the key value pairs and make a brand new one. And since this is an array-based structure, it has finite size. Eventually, you might run out of size, and then you need to do a grow operation. You need to resize the whole thing. So then, with get, you just start at the beginning and loop till the end. And once you find it, you can return its value. For contains key, similar to get, you just scan all the pairs, return if it's found. Remove, we're going to be a little bit clever. So for remove, you're going to have to still do a find. You're going to have to go find where the key value pair is. It might not be there, and so you don't have to do anything. But once you find it, one thing you might think is to shift everything over like we would an array list. And you definitely could do that. But we're going to be a little bit more clever here. The reason is we don't actually care about the order of the key value pairs. There's no invariant that says the first key value pair put in should be at index 0. So instead of doing all this shifting, we'll just move the last key value pair and just plop it in the place where we just removed a value. So when you do put B97 as a concrete example, you're going to loop through. Once you find the key with the B, you'll replace it. When you put E20, you'll move it all the way over there to the end because you have to go all the way to the end to find that the E was not there, and then you put in the empty spot. If you ran out of space already, you'd have to do a resize. If you're going to do a remove, say you want to remove the key B, well then you need to remove it. And then instead, like I mentioned, instead of shifting everything over, you could just take the E key and put it in that place. Now you have a free spot at the end. There's a little subtle detail, but I thought I should point that out because it's a little bit different. And you can already see on the right-hand side of the screen that the way I'm going to talk about the big O analysis is already going to be very different than what we saw before. For big O analysis, in this context, it really depends on where the key is in the dictionary. And the example I have on top is kind of the worst case scenario. Like, what if the key is the last one in the dictionary, or if it's just not in there at all? And then there's kind of this best case scenario where the key I'm looking for is at the beginning. Both of these are cases that could happen, so they're both valid. So let's look at them both as a bit of a preview for what we're going to talk about later this week. The put call in this array-based implementation is going to take O of n time, and it's going to take linear time. Why is that? Well, this is in our worst case, where the value we're looking for is really at the end, or maybe not even in there, which means we're going to have to loop from the beginning all the way to the end, meaning we're going to have to do about n steps, so it's a linear operation. And then, even if it could also be the case that we have to resize, which is another linear operation, so put is going to take linear time. Get, similarly, will also take linear time. Why? Well, to do get, we have to start at the beginning and go all the way to the end, and this is our worst case world, where we have to loop through every element. Similarly, contains will be O of n, and remove will still be O of n, even with our clever optimization where we just put the value at the end in that spot. Removing a key value pair still requires finding it. And since it's in this worst case world where we have to loop all the way to the end, it's going to be about n steps, so we're already at a linear operation, and then we can just remove it. So that clever optimization doesn't help us. And then size is going to be O of 1, because we stored the size field, we just keep track of the size. Okay, so now, thinking about big O analysis for this best case world, where we have the key we're looking for is in the first entry, put is going to be O of 1. Now, think about this for a second. Why is it O of 1 and not O of n if you have to do a resize, and then O of 1 otherwise? Well, the reason is the key we're looking for is the first one that we look at. It's the very first entry. We know it's already there, so we're not going to create a new key value pair. We're just going to put the new value in this current existing one. So we're never going to reach a spot where we ran out of room because we already have an entry for that key there. Get, similarly, will be O of 1. It's going to be at the beginning, so we're going to exit the loop right away. The loop to find. Contains key the same. Remove is now gets to be O of 1, because that find operation to find the key just takes one step to find something at the beginning. And then we get to use that clever swap optimization, where instead of having to shift all n elements, we just take the one at the end, just one of them, and put it in this spot. And then size is similarly O of 1. So now let's think about, now that we've seen how to do this with an array, let's think about the linked implementation. With the linked node implementation, it's all going to be basically the same as the array one, and everything we've seen so far in this class. So I'll go through this one today. So I'm going to go through this one just a little bit quicker. A couple things to note, though. The first is that to keep things simple, we're only going to keep track of the front. We're not going to also keep track of the back. And then we're going to still keep track of the size. And all of the operations are going to behave just like you'd expect if we used everything we learned about comparing array and linked operations before. Put, you just loop through till you find it, and if it's there, you just change the value. If it's not, you go to the end to add a new key value pair. Get, you have to go find the key value pair. Contains key, you find it. For remove, you have to find it, and then, worst case, you have to go all the way to the end and remove it, or the last one, or nothing. Or maybe it's in the middle or the front, and then it's just a couple rearranging of points. And similarly, we're going to have these two cases to think about for big O analysis. And I'm going to go through this one just a little bit quickly, just because we've kind of done a lot of these before. But for example, our put operation for real quick. If you do contains key, you're going to search through till you find the C. You get D, you're going to go all the way to the end. And if you put B, since you found B somewhere else, you're going to change its value. The runtimes for these in this worst case world, where the key value pair is at the end or just not in the dictionary at all, put is going to take linear time, get will take linear time, contains is a linear time, and so is remove, and then size still gets to be fun and constant time. In this best case world, don't worry if the key we're looking for is at the very front. Put, get, contains key, and remove are all constant time. Remember, removing from the front of a linked list is very easy. You just change the front pointer. You don't have to do any looping or anything like that. And size still gets to be constant time. So it's very similar to everything we've seen before, but it's still a useful exercise to think about these two cases, because this is a bit of a preview for one of the tools we're going to use when thinking about how to analyze code more rigorously than this kind of hand-wavy thing we've been doing so far. Now, one thing I want us to think about is what might happen if we delete the size field. So what if I told you I don't want you to have a size field in your linked map implementation? The first question is this okay? How could we implement size to return the count of the keys? Well, it turns out this is okay, because our map wants the abstract state of the number of keys, but we're still able to answer that with this concrete implementation. We just have to count the number of nodes in our list. So this is still doable. Now, would you ever do this? Because if you're going to do this, it's going to increase the runtime, because now size needs to loop through the whole list to count how many nodes there are. So now both the size operation and both the best and worst case are still O of n. They're still linear, or now they're going to be linear time, which is just bad. And the answer here is possibly. If you care a lot about storage space, meaning that the cost of storing an int, which is only a couple bytes, is so high that you just can't have it, well, then it might make sense. It might make sense to save that little bit of space for the increase of time. But probably for most contexts, that's not a useful trade-off, because 4 bytes of memory is basically free. But on some systems, it might be constrained. So again, thinking about design decisions, thinking about what is the pro and con of doing this, and does this actually help us? And again, there's not necessarily a strictly this is the right answer. It all depends on context, whether how much you value space versus time, which is a value judgment you have to make based on your context. So with all of that, I have some key takeaways for us. We've seen how different implementations can make huge runtime difference for the same ADT. A queue with a resizable array where we had that wrong invariant could be so much slower than a linked implementation of that queue. Many of these ADTs and data structures may be review for you. Maybe some of the terminology we use is different, but either way, the skills that we've been developing so far this quarter about determining and comparing runtimes is kind of the real goal here. I mean, the first goal is definitely review, because for a lot of students, they haven't seen this stuff in a while. So hopefully this review has been helpful. But another big goal here is to get you in the practice of thinking about runtimes, because that's what we're doing for the rest of this week. And we hopefully pointed out that you might have to start seeing that analyzing runtimes is not as simple as we made it seem in 143. One operation can have multiple big O complexity classes depending on the situation. And it's harder for us to go further without a more thorough understanding of this big O notation tool. So next up, and I forgot to change the date of the slide, it's for Wednesday and Friday, we're going to do algorithmic analysis, talking about more rigorous ways of actually analyzing what these runtimes will be and how to deal with these different cases. So with that, that's all we have for today, and see you next time.